Welcome everybody to our 8th webinar on the evaluation of soil liquefaction using the CPT. This is part 2 of a 3-part series. We had part 1 last week, and part 3 will be held a month from now on July 12th, but we'll remind you about that a little bit later. Feel free to use the questions section in the GoToWebinar control panel to type in any questions during the presentation. I'll be writing those down, and we'll have Dr. Robertson answer as many as he can at the end. And I hope you enjoy the webinar. Here is Peter Robertson. Thanks.
Well, good morning. Welcome. Thank you for attending. And from the look of that poll, it looks like quite a few of you did watch part 1. So this is going to be about the evaluation of soil liquefaction using the CPT, and it's part 2. And part 1, we went over some of the definitions of liquefaction, and but most of part 1 was how the CPT can be used to evaluate cyclic or sometimes referred to as seismic liquefaction. And so just a reminder again of the definitions. Seismic liquefaction is where you get cyclic loading. That cyclic loading, particularly from an earthquake, covers a very wide area, so all the elements are exposed to it very quickly. So it's essentially undrained loading, and that cyclic loading tends to induce a buildup in pore pressure. That buildup in pore pressure reduces the effective stress, and for level or gently sloping ground, essentially you can reach a condition of zero effective stress. And when you get zero effective stress, you get very large deformations and hence cyclic liquefaction. Now, flow liquefaction, which is what we're going to talk about today, is built around the concept of strain softening. And in fact, Terzaghi, over 60 years ago, had identified this, and he used the term spontaneous liquefaction. But today we'll use the more generic term of flow, or sometimes static liquefaction. And I think, as I said last time, I'm not a big fan of the use of static liquefaction, because you'll see that about 50% of the case histories were actually triggered by cyclic loading, mostly earthquake loading. And so static liquefaction can be a little bit limiting in its description, so I tended to prefer the use of flow liquefaction. So just a reminder again, so last time we talked about cyclic liquefaction, and as I said, this is the condition of zero effective stress due to undrained cyclic loading, and you need shear stress reversal, and that occurs pretty well everywhere. Essentially on level ground conditions or gently sloping ground, but in big earthquake it pretty well occurs in most places. In the resulting liquefaction and the resulting deformations are controlled by the size and duration of the cyclic loading. So a larger magnitude earthquake typically lasts a little bit longer, more numbers of equivalent cycles. And of course, the closer you are to the source of the earthquake, then the higher the intensity is, and so the bigger the cyclic stress ratios are. And you can get very large deformations, as illustrated from some of these photographs. Now, for flow or static liquefaction, you need a strain softening response in undrained shear, and I'll describe that in more detail. You need a trigger mechanism, something that's going to trigger it to strain soften, and you need the static shear stresses to be greater than the minimum, or sometimes referred to as the liquefied undrained shear strength. Traditionally, sometimes it was referred to as residual undrained shear strength. I don't like that term because that has a specific meaning in relation to the very large strain undrained strength of clays. So liquefied undrained strength is probably a more generic term. And then you need a kinematically admissible mechanism. So you need to have enough of this material that strain softens so that instability actually gets triggered. And when instability gets triggered, you can actually have uncontained flow. You can have very large deformations. Or if only a small amount of material strain softens and it's surrounded by strain hardening material, then some of the load can get carried by that strain hardening material. So it may deform, but the deformation ends up being contained, and it's not a large-scale flow slide. So you can see it's quite a complex mechanism. So here's a schematic of the undrained response of saturated, contractive, sandy soils. And on the left, you see a sort of generic stress-strain curves starting from an initial static shear stress and then rising to a peak and then strain softening to some liquefied undrained strength. And you can see here it's trying to illustrate the variety of triggers. You can have a sort of a static trigger, or you can have undrained creep or deformation from A to D, or you can have cyclic loading that might trigger that strain softening. And you notice here that the cyclic triggering is not exactly the same as seismic liquefaction, because you're not reaching a condition of zero effective stress. You're just developing enough pore pressure or strain to trigger the strain softening. That's illustrated here on the right with the stress path. So here's a stress path. So ABC is the static constant rate of loading stress path. So you can see it rises to a peak and then strain softens. And you see a very large buildup in pore pressure as the effective stress reduces from A all the way down to C. And C can be considered to be its ultimate state, or sometimes referred to as critical state, which we'll talk about a bit later. And some people have referred to the peak point. If you had a series of tests that you could join them up, and it essentially defines a yield strength envelope, or more precisely a yield surface, and that when the stress path hits that yield surface, it triggers strain softening. And again, illustrating it can be by undrained creep or deformation that gets it there, or by cyclic loading. Or another form of loading, one that's quite dangerous for large structures, particularly earth dams or tailing structures, is a relatively steep slope and then a rising phreatic surface. And so you might be at point A, and as the phreatic surface rises, the shear stress stays essentially constant, but the effective stress decreases. And then when it hits this yield strength envelope, or the yield surface, then it can trigger undrained collapse. And so people have done experiments where that loading from A to D could occur in a slow drained manner, and then at point D, collapse occurs, and then essentially triggers rapid undrained loading down to the liquefied strength at C. So you can see quite a complex mechanism. So back in the 90s, when we had the research project called CANLEX, the Canadian Liquefaction Experiment, we did develop this sort of simplified flow chart that said, first of all, you want to characterize the material behavior, and it can either be generically strain softening or strain hardening. If it's strain softening, then of course you can have flow liquefaction. You can have either a monotonic or cyclic triggering. You need the gravitational shear stresses to be larger than the ultimate undrained shear strength, and then it can either be contained or uncontained. If it's uncontained, then you can get the potential for progressive failure, and of course deformations can continue well after triggering. So once you've triggered instability, deformations then continue afterwards. So if the triggering is seismic, the earthquake may actually end, and then failure may occur after the earthquake. But you can have either strain hardening or strain softening material, and if you've got cyclic loading, it depends on the size and duration of the cyclic loading, and if there's shear stress reversal, which for big earthquakes means you get that most places, you can actually induce cyclic liquefaction, which is what we talked about last week. And you can get large deformations, but the deformations essentially stop after cyclic loading, because the deformations are caused by the ratcheting effect of zero effective stress during cyclic loading, and therefore the deformations essentially occur during cyclic loading. But one of the things the flowchart also identifies is that you might have a material that's initially strain hardening, but because of a large earthquake loading, you induce cyclic liquefaction, you get large deformations. And then there may be pore water redistribution, and that may cause some of the surrounding soils to become looser, and then ultimately become strain softening, which could then subsequently trigger flow liquefaction. Now that's quite a complex situation, where initially you may characterize the material to be predominantly strain hardening, but that cyclic liquefaction could in fact trigger a strain softening response and then a subsequent flow slide. We'll come back and discuss this a little bit later at the end. So when it comes to flow or static liquefaction for relatively steeply sloping ground, so in general, steeply sloping ground is anything more than about 5 degrees, so earth embankments, dams, and even gently sloping submarine slopes, etc. Now, the sequence to evaluate flow liquefaction is a little bit different. First of all, you want to evaluate whether or not the materials are susceptible to strength loss. And if they are susceptible, rather than just then determine will they get trigger, is often then evaluate the stability, assuming that they do strain soften. And then if stability is unacceptable, then evaluate whether or not the triggering will actually occur. So the sequence is a little bit different from cyclic liquefaction. Now, if soils are susceptible and instability is possible, in other words, when you've used the, here it says post-earthquake, but basically the strain softening liquefied undrained strength values, if you use those values and stability is significantly less than a factor of safety of 1, then often it's prudent to assume that triggering will occur, because case histories have shown that sometimes it's very minor triggering has caused instability. And again, we'll mention this a little bit later. So evaluate susceptibility for strength loss. Soils must be strain softening and undrained shear. Now notice it doesn't say sand or clay, so this can occur in very loose sands, very loose silts, and very sensitive clays. So it's not limited just to sands like the seismic liquefaction tended to be limited to. Now, strain softening soils are contractive at large strain. So you saw that when they strain soften, that means you get this large buildup of pore pressure in undrained shear. And of course, you're getting a large buildup in pore pressure because the soil wants to contract. Notice I'm being a little bit more precise here. It says contract at large strains. So can we identify soils that are either contractive or dilative at large strains using the CPT? And the answer is yes, you can. I'll give you a little bit of background. So we'll talk just a little bit about state parameter, primarily applied to coarse-grained soils. So Bean and Jeffries were one of the early people to suggest this concept. It came out of critical state soil mechanics, and it's illustrated here in a plot of void ratio against log mean effective stress. And the critical state line is sort of identified as essentially a straight line. And if you're loose of critical state, then you're essentially contractive. And if you're dense of critical state, you're essentially dilative. And they defined a state parameter as essentially the difference in void ratio that you currently are from the void ratio at critical state at the same mean effective stress. And so if you're loose of critical state in drained loading, that would mean that the soils would contract and change in void ratio towards critical state. But if you loaded them undrained, then that contraction will build up pore pressure, and so the effective stress path will move to the left towards critical state. And so there'll be a large decrease in effective stress, and because you've got the strength envelope, then you, of course, a large decrease in the undrained strength. And of course, the reverse is true if you're dilative. Now, Bean and Jeffries and others recognize that the critical state line is not a straight line over a very large stress range. And so Professor Bollinger did quite a nice job. He combined all of the work that Bolton did that sort of linked the dilatancy of sands to friction angle and relative density. And so Professor Bollinger suggested sort of a modification that talked about this relative state parameter, where instead of difference in void ratio, it's essentially a difference in relative density. You know, the relative density that it is in the ground reference to its relative density as critical state lines. It's a slight modification. And by combining it with the Bolton's genericity, all of Bolton's work on sands, he was able to essentially define a generic critical state line for sands. This is for silica sands, where Q is equal to 10 in Bolton's relationship. And you can see I've superimposed the straight line from Bean and Jeffries across, and says, you know, well, for loose sands and for low confining pressure, you know, the straight line is a reasonable representation. But when you go to very high confining pressures, it does curve over, you get grain crushing, and so there is a difference in response when you get to very high stress levels, and we'll maybe come back and talk about the implications of that a little bit later. So Bean and Jeffries essentially have devoted you know, the last 30 years studying this topic, and they wrote a book, I think it was called liquefaction, a critical state soil mechanics approach. So it's an excellent summary of their work, and it illustrates that the problem is complex. It depends mainly on the in situ stresses, and we mentioned that last time, that although we tend to normalize the cone data with vertical effective stress, we recognize that it should be mean effective stress, or sometimes horizontal effective stress. So it's not just the vertical effective stress. It's influenced by the shear stiffness, particularly the small strain shear stiffness, the shear strength, compressibility, and plastic hardening. And so Jeffries and Bean suggested that really it needs a combination of in situ tests, and they recommend the seismic CPT because you can measure the shear wave velocity and get the small strain stiffness as well as the CPT data. And then combine that with some lab testing on reconstituted samples to determine the critical state line of the soils. Of course, if you've got a very uniform soil deposit, that's relatively straightforward. But if you've got a highly variable soil deposit, then that can be quite complex about how you determine the critical state line for all of the different variations of soil. But based on extensive calibration chamber results and some of the Canalex data where we got frozen undisturbed samples, as well as lab testing and numerical simulation, it is possible to estimate the state of the CPT, and a number of attempts have been done. Probably the first attempt to do this was Pluis et al., and then Jeffries and Bean themselves did it. And then I sort of updated it a little bit. I sort of put contours of state parameter on sort of the normalized soil behavior type chart that I tend to use, which is just normalized cone resistance against normalized friction ratio. And so you can develop a set of contours that define state parameter. And you can see that zero state is down low here, and then as more dilative state, you progress up the chart. So the denser the sand gets, obviously the more dilative it is. And what this illustrates is that you could have two soils, essentially a clean sand at a given state parameter and given cone resistance, that's going to have the same state as, say, a silty sand that has very different CPT values,